All right. So I'm Dan Fried, Director of the Harvard Center of Mathematical Sciences and Applications, the CMSA. It's my pleasure to welcome you here this afternoon. The center is a mathematics center at Harvard devoted to the two-way interaction of mathematics and science, and the ways in which the power of mathematics applies in all sorts of sciences, but in the other direction, lots of ideas and concepts and even tools come into mathematics from outside of mathematics. And one of those tools is machine learning, very topical, coming into science in all ways. And it's a very active topic to investigate how it might be used in mathematics. So we're having a 2-month program in September and October at the CMSA on the topic. Lots of activities you can find on our website. Today, we're happy to have one of the co-organizers, Geordie Williamson from the University of Sydney. He's a world leader in geometric representation theory, and he'll tell us about whether AI and machine learning can help with hard mathematics.
Thank you very much, Dan. Also, I'd just like to thank the CMSA for the opportunity to take part in this really amazing program. So I think Francois keeps repeating that he thought it was going to be good, and it's a lot better than he expected. So I've really been looking forward to this for a year or so, and it's amazing to be here. So I want to start with a quote that I love from Barry Mazur, who's a professor here. And he says that mathematics is humanity's longest conversation. Okay? So we've been having this conversation for over 2.5 years, perhaps longer. And we're at this kind of extraordinary point in history where this conversation is interacting with the ideas of modern artificial intelligence, which is an extraordinary kind of moment. And I think no one can really predict what's going to happen in this conversation, but it's really, we're seeing the birth of a field, I think. And it's very amazing to kind of happen. So just to put the AI and mathematics in context, let's start with a bit of history. So this is Alan Turing. Okay, so he was born and raised in the United Kingdom. And he gave us the first mathematical conception of what it means to compute. It has a definition. He defined what a Turing machine is. And at this point, there were no actual physical computers, but he was the first one to formalize what it is a physical computer could potentially actually do. And then his work was interrupted by the Second World War, where he changed direction and he worked very intensely at Bletchley Park on the effort to decrypt the German. Experts say that it's very hard to know, but he probably saved millions of lives through his incredible contributions to Bletchley Park. And then it's very interesting after the end of the Second World War. So suddenly, for a brief moment, his contributions during the Second World War were enormously appreciated, and so he had a lot of freedom. But he also couldn't talk about anything that he'd learned at Bletchley Park, and also had a lot less resources. So he spent this famed sabbatical in Cambridge, where he was basically able to think about what he wanted for a year. And this was when he started conceiving of artificial intelligence. So he called it machine intelligence. Okay. So there's this amazing 5 years where he started thinking seriously about what it would mean to have an intelligent machine. And he also came up with the Turing test. So he wrote this article in Mind, which is a philosophy and psychology journal, where he proposed the Turing test, which is a purely empirical measurement of intelligence. If something behaves in a way that we can distinguish it from something that we think is intelligent, then that thing is intelligent. And that made an enormous kind of contribution to philosophical study of what it means to be intelligent. And yeah, so I want to emphasize that Turing was trained as a mathematician. He was interested in mathematical ideas throughout his life. And so this is this technical report. So it wasn't published during his lifetime. This is the report that he produced in his sabbatical in Cambridge. And it's the first article that takes the prospect of AI seriously. And it's a really extraordinary thing to read. And amusingly, his boss was very unimpressed. He kind of said to him, I kind of hope you'd do something a little bit better with that 1 year that I got you of free research, okay? So here's a picture from intelligent machinery, and you have the first picture of the first idea of a neural network. So he says, we're making these organized machines. So at Bletchley Park, he had the first glimpse of what a computer might be like. He didn't have access to a computer. And then in these 5 years from 1945 to 1950, he actually had access to one of the first computers. So it was very much delayed, but he was one of the first people to actually program a computer. And he's like, okay, when we're building these computers, we're doing it in a very organized fashion. Well, what happens if we connect things up randomly? And then he says that the brain of a child is an organized machine. And then slowly the process of learning is organization, which is very close to our modern conception of training of a neural network. And then he says, imagine that we have such a thing. What would we use it on? He says, let me come up with a few possibilities. Games, languages, translation, cryptography, and mathematics. It's a pretty mind-blowing list of 5 things if you look at the history of AI. Yeah? And the only thing that he mainly was a little bit off on was cryptography, but he don't figure that. And I just want to highlight mathematics here because I think that throughout the history of AI, mathematics has been a critical litmus test for the development of AI. So as I mentioned, he then wrote this article in Mind, which was basically trying to convince people to take the prospect of intelligent machines seriously. And I'd really recommend, if you haven't read this article, it's very, very interesting to read. It's also very funny. So at some point, he's proposing the Turing test, and he says, okay, we put some engineers in a room, and they should build a machine that can fool us into thinking that it's intelligent. Just through, like, we communicate through a third interlocutor. So we write messages, send it to the machine, it comes back. It should convince us that it's intelligent. And he says, how about solving this? And he says, well, the obvious solution is 2 of them get together and have a baby and wait 10 years. Okay. And then he says, I explicitly disallow that solution. Okay. Also, towards the end, there's a very funny bit where he says, the statistical evidence for telepathy is overwhelming, and I find that a little bit hard to deal with. And okay, so it's quite a remark. I mean, it's very, very, very interesting article to read. I just want to emphasize this, like this quote from Robin Gandy, who was one of Turing's friends, where he said that Turing had a lot of fun writing this article, but also he wanted to convince people to take the prospect of intelligent machinery seriously. And it's interesting because I feel like at that point, no one listened, and Turing was very much alone, but now we have to take this prospect seriously. This is finally 70 years later, or 75 years later, we're starting to take this prospect seriously. Okay, so what the point of this talk is to say 3 things. So basically that, firstly, that mathematics provides a very interesting lens through which to view AI. So, you know, I feel like we're all getting bombarded with this hype from AI, and so it's very hard to kind of stand on your feet when you're getting bombarded with all this stuff the whole time. Very hard to see what's going on objectively, and mathematics provides a very nice way to do so. And also, everybody that I know that's thought about AI and mathematics kind of has to ask themselves what they're actually doing as a mathematician. And I think that's very interesting. And I want to try to emphasize that both of these points are true at a kind of large-scale sociological level, but also at a small-scale technical level. Okay? So the first half of this, or first third of this talk will be about sociology of mathematicians and AI. What is it we actually do? And what do we fear from computers and this kind of thing? And then I want to just give a lightning introduction to neural networks, and then actually give some applications of current applications of AI to mathematics. Okay. So now, This is the kind of broad bit. So what is it that mathematicians actually do? I think that, I've been a mathematician all of my working life, but I don't think that I really started asking myself this question for some time. So here's one answer. A mathematician is a machine. You insert coffee and theorems come out. Hopefully it's an intelligent machine. However, so it's certainly true that theorems are important, and it's certainly true for me that coffee is important. And I think it's clear that logic and reasoning are the kind of lifeblood of mathematics. So I think that you can imagine the experimental sciences without logic, like they would be very different, but they might still exist. Whereas I think that you cannot really imagine mathematics without logic or reasoning. And you might be familiar with Kahneman's distinction of the two types of thinking. So the system one thinking, which is the immediate thinking, so driving a car when you know very well how to drive a car, having a conversation in a pub with a friend where you're relaxed. And then there's system two thinking, which is where you really feel like you're thinking, like playing chess, solving a problem, the first time you learn to drive a car. So, and mathematics is often seen as the kind of exemplar of system two thinking. However, if you actually talk to mathematicians, you will learn that we spend a lot of time in a world governed by conjecture, by hypothesis, by heuristics. It can happen that a big breakthrough on a problem happens at a coffee table at breakfast or something. That a chance conversation, a remark, a mistake can be incredibly powerful in guiding our subject. So if you think about examples, analogy, intuition, conjecture doesn't really seem so much like system two thinking anymore. The other thing that I find absolutely remarkable about mathematics, particularly in contact with AI, is what I call its substance. Okay? So in school, we learn that the square root of 2 is irrational. And there's an old apocryphal story of Pythagoras. I have no idea if it's true, but it has an essence of truth, which is that Pythagoras could explain with a stick in the sand why the square root of 2 is irrational. So he can explain to his followers why the square root of 2 is irrational. And over 2.5 millennia of mathematics, we've constantly been changing our foundations. We've been constantly changing what we call mathematics. And yet this argument is still alive today and is still correct today, even though we've changed the definition of what it means to be a correct argument. Okay? So to use a kind of horrible analogy from computing, a program on a Mac just doesn't run on. And yet we're constantly changing the foundation of what we call mathematics, and still our subject survives. So there seems to be something that's there which we can't quite pin down, which is, I think, remarkable. So this is an example just to challenge the mathematician that all we care about is theorems. It's a kind of classical example. So the 4-color theorem. So you imagine that somewhat colorful picture on the right is the map of a very strange states in some very strange land. And the 4-color theorem is the statement that we can color this map with 4 colors so that no 2 states that share a boundary have the same color. So this is a major unsolved problem from about 1850 through to the 1970s. There were many false proofs of this statement. Several very good mathematicians gave incorrect proofs. And then it was solved by Appel and Harkin in 1976 using an extensive computer computation, so long that no human could follow it. And still today, there's no fully human proof. So at the time, it caused a lot of controversy. And there's a beautiful article by Thurston, it's called On Proof and Progress in Mathematics, where he discusses this example. And he says, it evoked much controversy. So he says, I don't actually think that mathematicians are doubting the fact that that's true. Okay? You know, I remember I'd have these conversations when I was a grad student. People said, well, maybe like a bit had flipped in one of the computations. And this just happens so rarely. I just found this argument incredibly unconvincing. You know, if you run it 100 times and it always tells you the theorem is true, then I believe the computer. Yeah? However, what Thurston says is that this proof reflects a continuing desire for human understanding of a proof, in addition to knowledge that the theorem is true. So there's something about mathematics that we really want to understand what is true, not just, we really want to understand the why, not just the what. So, you know, with kind of AI, there's this, people pose this thought that imagine that AI can solve a problem and we've got to understand the solution. And this has already happened and we've already seen how we react. Yeah. So formal mathematics is, traditionally, we would agree on some rules of mathematics and I would think I'd proved a theorem and I would send it to someone else and then we'd reach a consensus that a theorem is true. But then it's very tempting to say, can't we convince a computer that something is true? Okay, so, and that's been the recent progress. So now one can explain proofs to computers. It's still very difficult to do, and automating this process is a major challenge. And of course, with large language models, many people were jumping up and down saying, let's connect large language models with formal provers. And this hasn't worked so far, I would say. Yeah, so there's one maybe exception to that, but it's certainly a lot more complicated than hooking up a large language model to a formal prover. It's possible that this works, but it's definitely not as simple as people were making out, I think, when ChatGPT came out. And one thing that I find just extraordinary is, so I told you that Pythagoras could explain to someone 2,500 years ago why the square root of 2 is irrational on the sand. So if you actually do this in Lean, it takes 647,315 lines. 647,315 lines. Okay? So I find this absolutely remarkable. And it also kind of says that what we're doing when we're doing simple proofs is actually probably a lot more complicated than we give ourselves credit for. Okay? So this is another example of this substrate independence, that now this proof exists on silicon somewhere, not in our brains, and yet the statement remains and the proof remains. Okay, so now I want to get to this thought experiment of Akshay Venkatesh. So in 2017, our DeepMind beat some of the best humans at Go. And this was something that, so Go is this game, you know, popular in Korea and China and also popular in the West, which was thought to be intractable for computers. So much, much harder than chess. And it was solved by DeepMind's AlphaZero. And he asks, what would happen if the same thing happened in mathematics? And it's a very, very interesting article where he gives his version of what happens. Okay? And based on this very interesting discussion, he proposed a workshop on the changing face of mathematical research, which happened at the Fields Institute in 2022. And this was one of the most inspiring conferences I've ever been to. So I was saying before that I didn't think very much about what it is that mathematicians actually do. And at this conference, you had a whole lot of mathematicians like really thinking hard, not just mathematicians, also philosophers and anthropologists and things we actually do. And afterwards, there was two editions of the Bulletin of the American Mathematical Society that featured articles coming out of this conference. So this is just an example of the kind of changing face of mathematics, forcing us to reflect on what we do as mathematicians, that I think is very interesting to observe and to be part of. Okay, so I just want to point out three. First is by Michael Harris. Just the title, I think, expresses exactly what I'm trying to say. automation compels mathematicians to reflect on our values. Yeah. There's also this incredibly, I think, very interesting article by Ochigami talking about the evolution of proof in mathematics and the evolution of mathematics as a kind of anthropological phenomenon. So he's an anthropologist, and he basically points out things like, before we had a calculator, we had respect for people that could multiply large numbers quickly. And the moment we have a calculator, that ceases, we cease to regard that ability as being very impressive. And so you have this constant evolution of value based on our proof standards and based on our access to technology. Very, very interesting. And for the rest of the talk, I want to go in the theme of my contribution to this volume, which is basically how can techniques in deep learning help mathematicians today? So less speculative about the future and how can it actually help on concrete problems. Well, you tell me. I mean, I'm yeah, I mean, I think it's not so obvious. And I think the more you think about it, the more it's not obvious what it is that we do. So I know that's not a very satisfying answer, but yeah. I mean, I would really recommend the article of Thurston as a first step to thinking about this, and also the article of Ochigami. So I just have to discuss neural networks for a second. And you know what it means, then you've seen this picture and you know what it means. But if you haven't seen this picture, I'm not going to be able to explain what it means in what is meant to be a public lecture. Okay? So this is a picture of kind of the pistons of an engine or something. This is actually how to build this thing. I just want to explain to you what it does, what a neural network does. So I'm not going to explain this. I'm going to explain what a neural network does. So first, I hope you can remember a line and best fit. Okay. Cool. So there's a unique way to fit a line in the kind of best possible way through data. So, and no matter how often, so the video is a bit funny, but no matter how often we can do this, we can start with any line. And basically we imagine that there's kind of, one way to imagine it is there's little rubber bands attached from each one of the data points to your rod. And so the further away your rod moves from this data point, the greater the force exerted on it back towards the data point. And then it's wobbling around and it reaches an equilibrium very fast. That's a way to think about a line of best fit. So it's funny. So I grew up on a farm, and my father, like just when I was starting to become interested in mathematics, father said, 2 neighbors they've forgotten where the boundary of their property is. And there's these remaining fence posts. Is there some mathematical way of working out a good line through these fence posts? So the fence posts are not in line. And I said, yes, I can do that. I know how to do a line of best fit. Okay. So if our data set is not linear, then we can still fit a line of best fit. Okay. And it tells us something, but it's not really that instructive. And I think it's not difficult to imagine that now we can make this blue line out of some bendy material, some wobbly material. And we can do the same thing. We can imagine that all these data points are pulling on it in some way, and then we look at how it evolves, and we get something like this. Okay, so this is a neural network training. And now, I think the video is not coming through as well as on my laptop, but as you'll see it training, if you see it training again, you can see it jittering a little bit. So the line of best fit really just moves straight into position and locks there, whereas there's this jitteriness to neural network training, which is because we choose some subset of the data points and just allow them to pull for a somewhat technical reason. And so it's always jittering around, and this jittery nature is very kind of crucial. And this is what can go wrong. This is one example of what can go wrong. Many things can go wrong as opposed to a line of best fit. So this is where it starts to overfit. So it starts to kind of match the data too literally. So this is meant to be a rough picture of what a neural network does. And I want to emphasize that this is encapsulating a one-dimensional relationship. So we have a one-dimensional input and a one-dimensional output. We have X and Y coordinates. And typically, neural networks are very good in situations where it's very high dimensional. So you might have like a million dimensional inputs, like millions of real numbers rather than one real number. Okay. So this is an example of the type of function that a neural network is good at approximating. An image, so there might be 1 million or 10 million pixel values in this image. So it's an enormous number of real numbers. So, 1 million inputs, and then you want to output the probability that you think that this is a tiger. So these are the kind of functions that one typically learns with a neural network. Now, there's a very important type of neural network called a transformer. I don't say much about, but I just want to emphasize that in the case of an image, what we're putting in is pixel values. So these are something like real numbers. So these are numbers in, but we can also put into a neural network sequential input, like sequences of words, letters, numbers, like DNA sequences or something like that. And somehow this was a challenge for neural networks for a long time. And there was this kind of revolutionary architecture in 2017 called a transformer, which then spurred the large language model revolution. So these quite, I mean, it's a beautiful idea, and somehow the fact that these things can scale so large, I think, surprised essentially everyone. So I just want to emphasize that they're very good at taking sequential input. So translation of languages, simplification of sequences like sequences or something like that, one could use a transformer on. Okay. So this is the kind of picture that comes out of a transformer, that we have some sequential input, like an incomplete sentence, nobody expects A, and then a transformer will give a probability distribution over the next word, for example. Okay, so now I want to discuss applications to mathematics. And I first want to emphasize that this is a very young and this is just a very tiny view of some things that I'm familiar with in this world. So many of these are participants of the SIMSA program, many of these people. So this is some work we did some time ago. So this is the technique of, so one of the things that I probably should have emphasized when trying to explain what a neural network does is that it produces an approximation of the function, but it gives you no explanation as to how it's doing this approximation. It's just approximating the function, but there's no interpretability. So one of the things that you would like to know if you're a statistician, so imagine that you have some, for example, prediction of like, I don't know, high blood pressure or something, and you have many, many, many different factors be contributing. As a statistician, it's very useful to be able to say the following factors contribute more than the following list of factors. Yeah? So this is attribution techniques in statistics. And you can do the same thing in neural networks to kind of look where the neural network is looking. So this is a problem in pure mathematics, where we start with two permutations. You don't know what that means, and we associate a complicated graph. So this is a whole lot of edges and vertices, and we associate a list of numbers. And there was a conjecture that's been around for more than 40 years now, which is that there's a way of getting from this complicated graph-like structure to this list of numbers. And if you'd like an analogy, I think it's really useful to think about the left-hand side as being something like an image of a tiger, and the right-hand side as being the statement that it is a tiger or something. So the right-hand side is some very interesting distillation of information in that graph, but it's very unclear what it's actually picking up on. So this is the problem that you're faced with, or like I'm faced with if I want to kind of attack this problem empirically. I just have an enormous list, like 1 million or so, of these graphs and these list of numbers, polynomials. And how do we somehow get some insight out of this incredibly long list? So the first step that we did was we trained a neural network to predict these polynomials. So it's to predict these measurements. And it's really remarkable in that when we looked where the neural network is looking, there was some very clear structure in where it was looking. Okay? This is very unusual so typically when you do this attribution technique with a neural network, the results are not good. But in this particular case, the results are there's clearly something going on. Okay? And then this pointed us in the direction of a theorem. So there's an enormous amount of mathematical work in getting a theorem out of this. But we could do this over many months. Like the first 2 steps were rather quick, and then there was still a very, very large component of mathematician, i.e. me, at the end. Okay. So this has worked several times, and I think it's got a lot of potential. So the next thing that I want to talk about, it's very exciting, and we're working on it at the moment at CMSA, is this idea of neural networks as generators, as kind of pointing in the right direction in a complicated search space. So as an analogy, you've probably heard this thought experiment that you get enough monkeys typing in a typewriter, then at some point they're going to type a Shakespearean sonnet or something. And that happens with incredibly low probability. However, if you imagine that these monkeys are kind of somewhat intelligent and you can show them a whole lot of bad sonnets, then even though they're dealing with bad sonnets, still maybe they'll get lucky sometimes and write a good sonnet. That's the idea of these models. So this is a problem that I love. So what's the largest subset of an n by n grid without isosceles triangles? Okay, so you start placing these stones. So you can imagine this is something like a Go board, and we produce these black stones. However, the rule is that every time we place a new stone, we're not allowed to create a single isosceles triangle amongst the black vertices, these black stones. Okay, can keep adding points. And here I'm cheating, and I'm actually adding to get one of the best. I mean, this is the best one can do on this particular grid. So what I'm saying here is that no matter what triangle I choose, so here I choose a triangle amongst these black vertices, and the statement is that this is not isosceles. And this example, I think if you first look at it, you're like, surely I can sneak in another stone somewhere in order not to create an isosceles triangle. But in fact, you cannot. So I tried to add that red one there, and I immediately created this isosceles triangle. And the claim is that this one, like you cannot add any more stones. This is a maximal construction. So it's kind of unclear who first raised this problem. It was either Erdős, and then there was a variant of this problem posed by Wu and also by Ellenberg-Jane in 2019, so reasonably recent, either from the 1950s or recent. And this has deep connections to problems in additive combinatorics. So it's both highly addictive and connected to very interesting maths. And so what this technique looks like here is we generate a whole lot of bad examples without isosceles triangles. And there's several ways one can generate these bad examples. And now you can view these examples as being words in some language of interesting constructions. And you can train a very small GPT-2 style transformer. So this is a neural network. And basically, you're kind of showing a monkey a whole lot of bad sonnets and then asking it to start typing and see what it comes up with. And remarkably, in these examples, you often get the odd one that allows you to add more stones, and then you can get a very good construction. So it's kind of averaging across bad constructions to produce a good construction. So when I was a kid, I think Mum had this excellent technique of getting my brother and I out of the kitchen, which is she'd say, go and find a 4-leaf clover. And so we'd run off and we'd search for hours, and then finally we'd find one. But then after doing this for about a year or so, my brother and I found this like particular patch of clover where we had to look, but we'd find a 4-leaf clover with much higher probability. Yeah? And so then Mum would say, go and find a 4-leaf clover, and we'd run out and we'd come back within 10 minutes, and then she'd have to find another way to get us out of the kitchen. Yeah? So this is a kind of a way of finding a little patch where you're much more likely to be successful in this search. Okay. So also you can iterate this. So it's a little bit like you find some big patch that's like a little bit more profitable in terms of 4-leaf clovers, but then you can search within that patch and then find a patch within the patch and iterate. And on several problems, this works really strikingly well. Okay, so this is actually what we're working on. One of the things we're working on here at CMSA. And I just want to emphasize that the techniques from AI are very standard by now. So it's not like you're not using some very tricky new thing in AI. The technique is standard. The mathematics is interesting. And I also think that this particular thing has potential applications beyond mathematics. There's many problems that involve some kind of discrete combinatorial search. And it's possible that this works well in some of them. So I love this quote from Gil Kalai: the methods for coming up for useful examples of mathematics are even less clear than methods for proving mathematical statements. So, I think that there's a big emphasis on proof, but also sometimes conjectures are just wrong, and you need to find some incredibly interesting example. Okay, so the last example I want to discuss is this example that I wasn't involved with, which is AlphaGeometry, the DeepMind team. So here the focus is on geometry problems like in school, but very hard geometry problems like in school. So if you remember back to geometry in school, if you can remember, there's very simple problems that you can just apply. You can just apply axioms, you can just apply things you know, and you immediately are led to the solution. But very few problems are of this form. So you have to do a construction. You have to have an idea. So just as an example of this, imagine that you're given an angle, ABC up the top, and you want to prove that ABC equals BCA. So the left angle and the right angle are the same. Okay? We know that this is a fact in isosceles triangles, but how do you prove it? So you prove it by having the brilliant idea of constructing so you put D midpoint between B and C, and once you've had this idea, then things are just formal from then on. Then you can just reduce down. And this is these geometry proofs that you often have to have one or two ideas, and then there's a formal business. So what the AlphaGeometry team did is they generate 1 billion triples of premise, conclusion, and proof. So this is, I won't go into how this is generated, but this is not generated by any kind of human input. So it's just a kind of random generation. So this is very similar to the previous example in that almost all of these are kind of very bad theorems. Yeah. And you're just giving the transformer a whole lot of bad stuff. And now you train a transformer on these triples. So this is, again, sequential input, and you can train the transformer on these triples. And now, if you've got premise and conclusion, for example, you've got the top there, let ABC be any triangle with ABAC, prove that blah. So that's a premise and a conclusion. You see what the transformer suggests to do. And in many, many, many cases, it makes a bad suggestion. But then occasionally it makes an excellent suggestion. Okay? So this is again, it's an enormous amount of sampling, but and you can imagine that this is a little bit like how creativity works. that creativity is not a mystery, that it's just a lot of sampling with experience from our environment. And this solves a large number of Olympiad problems. So this is what I think one of the most complicated ones that they were able to solve. Okay. So just in summary, I think this mathematics provides this fascinating lens through which to view AI, and AI provides a very interesting lens through which to view mathematics. And that these attribution techniques and transform, they appear to provide really interesting new tools for mathematicians to use. So this is from Turing. This is the last sentence of Computing, Machinery, and Intelligence. We can only see a short distance ahead, but we can see plenty there that needs to be done. So thank you.